right, welcome back. So I know that that last video about sort of introducing the concept of vectors and coordinate systems, that's a tough one at first to get this idea of representing things, motions, just with little arrows and sort of really stepping away from the actual object that's moving and thinking of some different concepts that underlie how it's moving. Like I said, the idea of using an arrow to represent something's motion kind of makes sense. We're starting to talk about adding these arrows together, adding these vectors together. It gets a little bit different. So what we're going to talk about in this one is more about using graphs, because that's kind of the next step. Once we get these ideas of some of these vectors and how things are moving, how do we start to plot some of these things in a graphical sense and to use these as pictures for us to be able to interpret something's motion. So in this particular chapter, we're going to be doing position time graphs. Now later, we'll be talking about velocity time graphs and acceleration time graphs. There's other kinds of graphs that's out there. These ones here about position and time. So when we're doing position time graphs, keep in mind a couple of things in mind. That this one down here is always going to be time, is always going to be the x-axis. And then this one up here is going to be position or displacement is typically what we end up doing up here. So this one's going to be in meters. This one typically is in seconds. So displacement in meters and time in seconds typically. And I'll leave my graph here set up in the normal kind of positive directions that this is considered positive and this is considered positive. It makes our lives easier in terms of what we're going to do. But positive isn't necessarily this cat moving to the right. Positive could be the cat moving to the left. It's just how we're drawing it. We're trying to sort of really abstract this object's motion. So let's say I do have my little cat here, and here's my little cat moving. So you can see here's my little particle model of my cat moving. Starting at time equals 0, 1, 2, 3, 4, 5 different seconds of motion. And then what the heck is this cat doing? So how do we kind of talk about where this cat is going? So think about if I plotted this so that each one of these dots was 1 second, and that right now we can say that this particular distance here, just for the sake of what we are doing, let's call this distance here 1 meter, just to make our lives easier. So we've got 1 meter, we've got a second meter, we've got a third meter, we've got a fourth meter, we've got a fifth meter like that. So moving pretty consistent, just regular kind of chill motion, right? So what would that look like over time? Well, if this here is t equals 0, and you'll see me use this subscript notation a lot, t equals 0, t1, t2, T3, etc. These are kind of common subscript notations that we use to represent the time. So time equals 0, we can say that it's at position 0. So we can say it's literally right there. And then at time equals 1, well, where is it? Well, its displacement from the beginning is now 1 meter. So at time equals 1, it's at 1 meter displacement. I'm going to do a little table like this. It'll make our lives a little bit easier. At time equals 2, where is it? At every particular second, it's basically moving forward 1 meter, right? That's kind of where it's going. So hold on. So this is a time and displacement or distance kind of thing. Time equals 0, its distance is 0. Time equals 1, distance is 1. Time equals 2, now it's gone 2 meters. At time equals 3, it's gone 3 meters, etc. What does this look like in the graph? Looks like this. 3, 4, and 5. So we've now taken this particle model and now we've turned it into a graph. And this graph tells us something about this, that this cat is moving basically every second. It's moving forward 1 meter. There we go. There's our position time graph. And it is going, by the way, this direction. That's the way that it is going. So now what? Let's say the cat stops now at this point and stays here, doesn't go anywhere else. So now at t equals 6, it's still here. T equals 7, it's still here. T equals 8, it's still here. T equals 9, it's still here, right? What does that look like in the graph? Well, if it's at the same spot for 3 or 4 or 5 seconds at t equals 6, what position is it still at? Again, this is distance, right? At 1 second, it's at 1 meter. At 2 seconds, it's at 2 meters. 3 seconds, it's at 3 meters. 4, it's at 4 meters. 5, it's at 5 meters. But now it's stopped. So at 6 seconds, it's still at 5 meters. And at 7 seconds, it's still at 5 meters. And at 8 seconds, it's still at 5 meters. And at 9 seconds, etc., it's still at 5 meters. So take a look at what this graph looks like. Okay, so now we've got a change in its motion, right? Here it was moving forward, and here it's moving Not at all, right? It's still staying at the same position. That same position, distance equals 5. So again, these look different, right? This is that particle model. This is a graph of its position over time. And you can see it right here. Its position is not changing. Slope tells us something important about how something's moving. Not only does this tell us where it is, but it tells us how it's moving. When this line is flat and horizontal like this, that means it's staying at one position. This is actually stopped, right? When it's going like this, and it's moving from position 1 to 2 to 3 to 4 to 5 over time, this is moving forward. And now what would happen if the cat was moving back? Cat turns around and goes back the other way. So now our cat's at position equals 5. And then it goes back to position 4, back to position 3, back to position 2, back to position 1, and eventually go back to starting position 0, something like that. So what's it doing when it goes like this direction? Now this way, it's not going necessarily backwards, but it's in the negative direction. So when we take a look at a position time graph, we can get some ideas about how something is moving. And again, you're reading from this just where is it versus what time is it. So this is actually graphing these two different dimensions at the same time, as opposed to this one up here, a particle model, really is just kind of graphing one at each dot is time, I guess. So you're turning it into a little bit of a different a picture. So let's take a look at a couple of examples. Now, what if we have our different cats moving at different speeds? Here we have the little orange cat. Here's our regular little orange cat moving about that speed. Da, 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 there he goes, right? Just a nice, 1 meter every 1 second. Okay, there he goes, right? There it is. Now, how about this cat? This cat's strolling, right? This cat's running. This cat's not going so fast. Maybe this cat, this is going 1 second. It's going 1 meter. Maybe this cat's not going that fast. Maybe this cat in 1 second, what would be slower? Maybe in 1 second, this cat's going half a meter, right? 1/2 of a meter. Or we could also say that it would be 1 meter equals 2 seconds, right? Both of these say the same thing. They're the identical qualities to it. So now if it goes only 1 meter every 2 seconds, well, what's that cat going to look like? All right, 1 meter every 2 seconds. All right, so that means 2 seconds, it goes 1 meter. And then 2 seconds, it goes another meter. And then 2 seconds, it goes a third meter. So again, if we did a little T-chart for this one, if I could draw straight, that would be helpful, right? If we had time and distance, every 2 seconds, it would go 1 meter. This would be 4 seconds to go 2 meters. This would be 6 seconds to go 3 meters, right? They go a different amount. It's not quite as fast, if you want to talk about it. So let's take a look at this graph. Okay. All right. So just like our previous one, this is still this upward graph tells me it's going in that positive direction, right? It's moving forward. But what's happening here? This is still going forward as well. But we can know that these are going different speeds. We know this because they're covering a different amount of distance in the same amount of time. In 1 second, or I should say, we can go over here. In 6 seconds, the little orange cat is going 6 meters. But in 6 seconds, the spotted cat in the middle is only going 3 meters. It's slower. So this is forward, slower, right? This is forward. I don't know if it's faster, but right? The slope tells us something about this. Again, slope is rise over run. And if we've got something that's got its distance here and its time here, and it's going more distance in the same amount of time, it's going faster. So velocity on a position time graph is slope. This is a really important concept that we use slope a lot in graphs in physics class, not just because we like to make you do y equals mx plus b. In fact, we rarely use that particular equation form in physics. At least our physics. So let's talk about our last cat, this little one down here. This cat's hauling some serious butt, right? I don't know if you've ever seen a cat just go like nuts like that. So let's say that this cat is going super fast. This cat now in 1 second, let's say it's going 3 meters. instead of 1 second is 1 meter, right? Or 1 second's half a meter. This cat's hauling 1 second's 3 meters, 3 times as fast as the first cat. In 1 second, where's it going to go? Okay. In 1 second, it's going to go 3 meters here. And in the second, it's going to go 3 more meters. 1, 2, 3. And in the third second, it's going to go 3 more meters yet. 1, 2, 3. So this is even faster. And again, just like we talked about earlier, when we're talking about slope here, this is the fastest one. So by taking a look at a position time graph and plotting these out, not only do we know something's not moving, which is a horizontal line, we can tell something about speed by the relative angle that it's going. We can tell just by looking at it which one of these cats is the fastest cat of this particular set. Okay, let's take a look at some of these other position time graphs, and let's talk about how to interpret some of these. So this is a great little graph here that's got a position side here. Notice it's got a 0 axis right here. So here's your 0 line, position equals 0. This means T, this is our time. So we're going forwards in time as we go. This direction is forwards in time. Always, we never really change that. But now we have a positive and a negative position. So what does that mean? All right, let's say right here, where I am standing, is my starting spot. We're going to call that position 0, right? Well, if I step forward from here, I would be going in the positive direction. If I come back to where I started, I'm at 0 again. And if I take a step backwards from there, now I'm going in the negative direction, right? I'm not necessarily turning around, but I'm going behind the starting line. So again, you can think about, like I said, as a starting position, if we say that this right here is, I gotta have to do this on my screen, right? That's that way, okay. So if this is 0 and I go this way, that could be the positive direction. But if I go this direction, it could be the negative direction, negative position. It's kind of like saying going north versus south or east versus west. So again, position. So let's take a look at interpreting some of these. And you can have a kind of a chance to take a look at it. There's 1, 2, 3, 4, 5 different individuals. There's a graph, person A, person B, person C, D, and E on there. So we can take a look at which one of these is moving forwards, backwards, fast, slow, not moving at all. So let's take a look at person number A here, or cat A, or whatever you want to call. So what's cat A over here doing? Okay, cat A. So at time equals 0, again, remember, this is time going left to right. At time 0, the cat is at plus whatever. And at time equals 1, and time equals 2, and time equals 3, and time equals 4, it's still at the same plus 5 or whatever we're going to call it. So here, if we're going to say this is 5 meters, this cat is at 5 meters, and 5 meters, and 5 meters, and 5 meters, and 5 meters. Horizontal slope means that this cat is holding still. So this one is not moving. Again, how do I know that? Because the slope of the line is equal to 0. It's staying at the same position, but it's at, I don't know, at plus 5 or wherever that position is that it wants. But it's in that positive spot. It's in front of that starting point. It's moved, ahead of wherever we're calling 0. But it's just not. It's just chilling there. It's not doing anything, but not moving. Okay, let's take a look at number. We want to do B? Sure, why not? Let's talk our way through B. So let's think about what position B is doing, because it's definitely a little bit of a funky one in terms of what it's up to. All right, so let's take a look at what B is doing. The easiest way when you're just starting off with these is to make a little position time table of some sort, so that you can kind of read what their positions are. So let's take a look at what B is doing. Okay, so we're talking about individual B, we're talking about time, and we're talking about displacement or position. So at time equals 0, where is this individual? Well, this individual here is at, what do we want to call that? -3. Sounds good. And then we can kind of do this sort of a thing. I'm going to do this, like that. Make some kind of fake timelines here. 2, 3, there we go. 2, 3, like that. There we go. So now we have kind of a grid. We can kind of read this. So at time equals 1, where is our individual now? Our individual was at -3, and now our individual is at -2, right here. And then at 2 seconds, now our individual is at -1. And at 3 seconds, our individual is at 0. Now, what the heck does that mean? Okay. What that means is that individual started behind the start line and is now approaching the start line, and at 3 seconds gets to the start line. Think about someone who's, like I said, literally starting from back behind. Okay, again, it's a little bit strange to think about that, right? If this is the start line, maybe this individual is starting here and is approaching the start line and now can move in front of the start line. It's kind of a weird idea. So where are we going next? Time equals 4 seconds. We are now at, say, +1. And time equals 5. We're at +2. So what does this mean? This means that the person has crossed the starting line. Whatever that particular starting line is, they've gone from the negative side of the starting line to the positive side of the starting line. That's what that means. So, and again, all they're doing is through time, they're approaching that starting line and then moving through it. That's all that means. So with this one, we can also tell that this is positive, right? It's a nice straight line. So they're moving forward. They've got some speed in that positive direction. And again, they're just moving from behind the start line, through the start line, and forward to the start line. Let's take a look at our next person. Who's our next one? We can take a look at part C. C is a little bit of a funky one in terms of what it's doing. So now, because C is doing something really weird. Okay, what is it up to? Notice how, first of all, it's not linear, right? It's doing something kind of weird where it's kind of flat, flat, flat. So like here, for these couple of seconds, it's almost like it's not going anywhere. So this is -3, this is -4, this is -5. So we could go, its distance right now is at -5, and then it's at -5, and then it's at -5. Okay, well, fine. And then it kind of moves up a little bit. So now maybe it's at -4.5, right? And then all of a sudden it starts to go kind of a lot faster, right? In terms of where it's going, it's moving up, but more quickly. It's covering more distance. It's really approaching here. So remember what our slope means. Slope this way means not moving. Slope this way means moving. Slope this way means moving faster, right? Slope kind of that way means moving slower. So what is this one doing? Slow, but getting increasingly faster. This part for C, it's moving towards the start line. So it's starting like 5 meters back and it's starting to sprint across as soon as it gets to the start line. And as soon as it gets here, it's going super fast, right? As it's moving, getting quicker as soon as it passes that start line. So it's kind of like getting a head start and running it through the finish line, start line, whatever you want to call it. So this would be speeding up, would be part C. Okay, let's take a look at our friend part D here and take a look at what D is doing. Okay, D, take a look at where it is. I'm just kind of erasing some of this other stuff that's out here. D is starting at position equals 1. That's where it's starting. And which direction is it going now? So this one is starting at position equals 1. That means +1 in front of the start line, right? So it's starting at +1. At time 2, time 3, it's at 0. So maybe this is +1/2. And then time 2, it's at 0, or at 3, it's at 0. Sorry if I got that time off on there. It's definitely a little bit funky in terms of where it is. It's going slow, right? It's not going very fast. So something like this. At time 3, it was actually at 0. So maybe this is plus a third, 2/3. This is plus 1/3, something like that, right? It's coming in kind of slow. Now it's going from +1 to 0 to -1, -2 as it's going through time. What does that mean? Okay, it's starting in front of the start line and going backwards behind the starting line. So it starts out at a positive position, gets to the 0 spot, and then keeps going the other direction. This could mean instead of going north, it's going south or something along those lines. It's changing kind of where its position is. It's crossing that finish line in terms of where we're calling the start point. So again, D is going backwards. B is going forwards. D is going backwards. This one's going in the positive direction, has a positive slope. D has a negative slope, so it is going in the negative direction, whichever that is. If it's toward the camera, away from the camera, to the right or to the left. It's just going the other direction. That's all that means. And it's going slower, by the way. If you take a look at the speed between B and D, B has got a steeper positive slope and D has a shallow negative slope. So they're going kind of different speeds. B is going faster forward, D is going slower the other way. And then our last one, our friend E here. E, okay, its slope is 0. It's staying at one position, staying at -3, -3, -3, -3, -3. It's just sitting there behind the starting line as opposed to in front of the starting line. That's all that particular means. So position time graphs. So with taking a look at these, you're looking at sort of where something is over time. You can use position time graphs to tell you about something's speed. The slope tells you about the speed. Whether it's in the positive or the negative side can give you some idea of which direction it's going, say to the right or to the left. And it can also kind of tell you where it is relative to if you have a starting spot like I said, like a starting line. I can tell you whether it's going in front of the starting line or behind the starting line. So there you go. Taking a look at some position time graphs. We'll take a look at these more in class for sure.